Hey everyone, this video is on thermal equilibrium. Thermal equilibrium refers to a state between two or more systems and objects where there are no heat exchanges occurring between them. And thermal equilibrium is established when these objects and systems share a common temperature. Recall that temperature is the measurement of the average translational kinetic energy of the molecules and particles in these systems. However, when we have two systems whereby one system has a higher temperature, energy will be spontaneously transferred from the higher temperature to the lower temperature system. This energy transfer is more commonly known as heat. The transfer will continue until the two objects will reach a state called thermal equilibrium at which they have the same temperature. In an isolated system, the total amount of energy before and after the heat transfer should be conserved by the law of conservation of energy. However, it's important to understand that although at thermal equilibrium the two systems will share the same temperature, the final temperature is not necessarily always an average of the initial temperatures of the two systems. This is only the case if the two substances that's involved in the heat transfer have the same mass and specific heat capacity. We'll discuss this in more detail later on in the video. The Zeroth Law of Thermodynamics states that when two systems are each in thermal equilibrium with the third system, then they are in thermal equilibrium with each other. This concept should be quite intuitive. If system A or object A and object C are in thermal equilibrium with one another, that means they have the same temperature. At the same time, if object B and object C share the same temperature or at thermal equilibrium, that means object A and object B should also have the same temperature and therefore be in thermal equilibrium with one another. Two identical metal blocks, block A and block B, have initial temperatures of 30 degrees Celsius and 50 degrees Celsius respectively. Both blocks are placed in contact within an isolated system. What will be the final temperature when thermal equilibrium is reached? Now we can assume the masses and the specific heat capacity of both blocks are the same, as we are told that they are identical. So we have block A and block B. Block A has an initial temperature of 30 degrees and block B has an initial temperature of 50 degrees. Heat will transfer from block B into block A as block B has a higher temperature. Now, by the law of conservation of energy, the energy that's released from B should be equal to the energy absorbed by A in the form of heat. The energy released by block A is given by Q equals to 𝑚𝑐Δ𝑇. Similarly, the amount of heat that's absorbed by block A is also given by the same equation, 𝑚𝑐Δ𝑇. Let's call this QA and QB to avoid confusion. Now, as we said earlier, by energy conservation law, the magnitude of QA should be equal to the magnitude of QB if we are dealing with an isolated system, because the energy that's released by B should be identical to the energy absorbed by A, as it cannot be destroyed. So then we can say the mass of A times by the heat capacity of A times by the change in temperature should be equal to the mass of B times by the heat capacity of B times by the temperature change of block B. Now, since the two blocks are identical and we are told that we can assume the mass and heat capacity of the two blocks are the same, we can cancel these variables on both sides, which means the change in temperature of both blocks should be identical. This is the reason why when we have two objects of the same mass and heat capacity, when they reach thermal equilibrium, the final temperature will be an average of the initial temperatures. In this case, the final temperature at thermal equilibrium for the two blocks A and B will be 40 degrees Celsius exactly. This means block B has decreased by 10 degrees Celsius, while block A has increased by 10 degrees Celsius. The magnitude of the temperature change are exactly equal. However, like I emphasized, the final temperature at thermal equilibrium is only the average of the initial temperatures for systems that have the same mass and heat capacity. Let's look at a different example. Suppose you have 0.2 kilograms of water initially at 20 degrees and a 0.3 kilogram metal block initially at 80 degrees. The two objects are placed in contact within an isolated system. After some time, they will achieve thermal equilibrium. What is their final temperature? So here, the metal, which has a higher temperature, will transfer heat to the water, which has a lower temperature. Let's call the amount of energy transfer Q. as they should be equal by the law of energy conservation. The energy released by the metal is given by minus Q, as it is being released, equals to mass of the metal of 0.3 kilograms multiplied by its heat capacity of 900 joules per kilogram and the changing temperature. So this will be the final temperature, which we're trying to work out, minus the initial temperature of the metal, which is 80 degrees Celsius. Similarly, we can write the same equation for water. Now for water, this will be plus Q, as it is absorbing the energy, equals to 0.2 kilograms of water multiplied by the heat capacity of water, which is 4,180, and then again times by the final temperature minus its initial temperature of 20 degrees Celsius. The value of Q, which is the heat transfer, should be equal in both equations, and the value of T final, TF, should be equal, as the two objects will come to a thermal equilibrium. So if we equate the two equations, we'll get minus 0.3 times by 900 times by TF minus 80 equals to 0.2 times by 4180 times by TF minus 20 degrees. Let's rearrange the equation and make the terms containing TF the subject. We'll have 0.2 times by 4180 TF plus 0.3 times by 900 TF. This is equal to 20 times by 0.2 times by 4180 plus 0.3 times by 900 times by 80. We can factorize TF on the left hand side. We have TF 0.2 times by 4180 plus 0.3 times by 900. If I type the right hand side into the calculator to get one number, this is 38,320. So finally, the value of the final temperature is 34.6 degrees Celsius. Notice how the final temperature is not an average between the initial temperatures of 20 degrees Celsius and 80 degrees Celsius. So to summarize, the final temperature at thermal equilibrium depends on the specific capacity and the mass of the substances involved in the heat transfer. In the previous example, the heat transfer occurred between two different substances, water and a particular type of metal. Now, water has a relatively large specific capacity than most metals, which means more energy is actually required to cause the same temperature change for water compared to metals like aluminium. So when the same amount of energy is taken out of the aluminium cup and put into water, we can expect that the change in temperature will be much larger for the aluminium cup, and the temperature change will be smaller for the water. In the previous example, my initial temperature for water was 20 degrees Celsius, and for the metal, the initial temperature was 80 degrees Celsius. If you go back to the calculation, our final calculated value for the final temperature of the two substances was 34.6 degrees Celsius. Notice how this final temperature is further away from the initial temperature of the aluminium and closer to the initial temperature of the water. This should make sense because aluminium has a smaller heat capacity, so it experiences a greater change in temperature compared to what the water has experienced, even though the amount of energy that's released by the aluminium is equal to the energy absorbed by the water. This concludes the video on thermal equilibrium. Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.